Yeah, the next talk is by Yogesh, and he will tell us about time and space complexity of query algorithms.
Good evening, everyone. I'm Yogesh, and I work in complexity theory in theoretical computer science. So I'll talk on time and space complexity of query algorithms. So let me start by defining what query algorithms are. Before I do that, the central question in theoretical computer science is about understanding computational devices. And so we mathematically formulate those computational devices and form these model of computation. And there are these various model of computations like Turing machines, quantum machines, communication protocols, and many more. The model of computation that I'll focus on today in my talk is this query model of computation. So this model is very simple model of computation and very concrete model of computation, yet it's very natural and powerful model of computation. So let me define what this model of computation is. So the setup is as follows. So we have a Boolean function on n bits. So this Boolean function might be encoding your problem. For example, let's say there is a n-node graph and you want to find out whether there is a k-click or not. You can encode that as a Boolean function. So this function is our problem, and this is known to the algorithm. What is not known to the algorithm is the input itself. And the algorithm does not know the input, but it has query access to the unknown input. So what it can do is, it can learn about x by asking queries of the form, what is the value of xi, what is the value of x5, what is the value of x3. And once it has enough information, the goal will be to output the value of the function while minimizing the number of queries. So goal is to output the value of the function on this unknown input by asking queries, and the goal is to minimize the number of queries while achieving this goal. So one can formally define what a query algorithm will look like. A query algorithm that computes your function has to output the correct function value on each x. And the query complexity of a function will be the query complexity of the best algorithm that solves your f. And the query complexity of an algorithm will be defined for the worst case input. So I've defined this d dt of f is the query complexity of your function. So let me give an alternative definition for this query complexity. Your query algorithm can be seen as a binary tree because you will form some strategy. Your strategy will look like something like this. You will query some variable, let's say x5 you are querying, and depending on the evaluation of x5, you will choose to query some other variable. For example, if x5 comes out to be 0, you query x4. If it comes out to be 1, you query x2, and so on and so forth. And once you have enough information that you are able to determine the value of the function, you will output the value of the function. So any query algorithm can be represented as a binary tree. And the number of queries on the worst case input will be the depth of this binary tree. So the query complexity that I defined in the previous slide can also be defined as follows. So it is like minimum depth of a binary tree computing f. Similarly, one can define size complexity of a function, which will be size of a minimum size of a binary tree computing your function f. So let me give you some simple examples. For example, let's say you want to compute and on n bits, which is equal to 1 if and only if all the variables are set to 1. So the following tree, you can easily verify that it computes your AND function. Whenever you see a 0, you know the answer of your function is 0. But as long as you see ones only, you have to query everything. So you can easily argue that this is optimal binary tree or optimal strategy or optimal query algorithm for the AND function. The depth of this tree is n, so your query complexity is n, and your size of this tree is n plus 1. So query can be thought of as analogously, like in informal terms, as a time complexity measure, and the size measure can be thought of as space complexity measure. Because if you'll try to store this strategy or this query algorithm, you would need like n plus 1 size, because you have this n plus 1 leaves are there and n nodes are there. So around like order n number of space you would need to store this algorithm. So this is another example. Let me skip this. So now that we have defined this query algorithms, let me also define randomized query algorithms. The algorithms which don't use randomization, I'll call them deterministic query algorithm. In randomized query algorithm, there are two differences. One difference is now algorithm also have access to unbiased points, unlimited number of unbiased points, although we won't need unlimited number of random coins. The second difference is the goal is relaxed a little bit. Now you're not, you can make some error. On an unknown input x, you have to output the correct answer with probability, with good probability, let's say 2/3 probability. And this should hold no matter what the unknown input x is. Okay, so that's our goal. And again, we would like to minimize the number of queries. Again, one can formally define the query complexity measures similarly. And one can again represent these randomized query algorithm as binary trees. The only twist will be now in the binary tree, there can be nodes where you won't query anything, but you might be just doing some random coin tosses. And based on the decision of those random coin tosses, you will choose to go either left or right on your binary tree. And remember, the goal is that no matter what the unknown input is, you would want to be correct with probability 2/3. Again, randomized query complexity F will be minimum depth of a randomized decision tree which solves your functions with probability, let's say 2/3. Similarly, randomized size can be defined. And we'll ignore coin tosses in this case, only query will be counted. Since I've defined my model of computation and these randomized and deterministic decision trees, let me start by telling about problems that we have been working on and the kind of results that we have obtained. The first problem that we have worked on is proving deterministic size lower bounds for composed functions. So for a Boolean function f and g of arity n and m, let f composed with g be a Boolean function of arity mn, where you first apply g on your input, and then on the output of g you apply f. So that is composed function, f composed with g. And now one can ask, like, can we prove deterministic size lower bounds in terms of properties of f and g? Okay. And with joint work with Meena, we were able to show that that the deterministic size complexity of f composed with g is exponential in deterministic query complexity of f and the rank of g, where this rank is a combinatorial parameter. I'll give you a proof by a definition by picture. For a binary tree T, rank of a binary tree T is the largest depth of a largest complete binary tree embeddable inside your binary tree, inside your strategy, inside your query algorithm. Okay. For example, on left there is a binary tree, and one can show that you can embed a complete binary tree of depth 3, but you can't embed a binary tree of depth 4. So rank of this binary tree is 3. And then the rank of a function you can define as a minimum rank of a binary tree computing your function f. So this is the rank parameter. So again, let me flash the theorem that I flashed earlier. So this size lower bound of the composed function is in terms of query complexity of f and the rank measure of your outer function g. So as a corollary, we obtain results like if f is composed with the 2-bit XOR, the size will be like 2 to the query complexity of f. Let me skip this iterated composed function, but let me mention this corollary because we'll again come to this. So this AND2 OR2, so iterated composed function is when you take a function and compose it iteratively some k number of times. Okay, so this f superscript tensor k is a notation which says f is composed k times. with itself. So this and2 or2, when you compose it log n times, using our theorem, you can prove that the size of this function will be 2 to the omega n. And this result earlier was known due to some other techniques by work of Jukna, Razborov, Savick, and Wagner. But this result now follows from our result as well, and we have now more general result about this. So the second type of problem that we have worked on is about the role that randomness plays in these query models. Okay. For example, one can ask what advantage does randomness buy us in case of query complexity or size complexity of a function. And there is this beautiful work of Nissan from 1989 which says that the deterministic query complexity and randomized query complexity can only be cubic apart. So which means that you cannot get a tremendous saving. They are polynomially related. Okay. And the size question, like you can ask the same question about size as well. This question has didn't garner enough attention before our work. And for this and or function iteratedly composed log n times, Sachs and Wigderson showed that the depth of this function will be n to the theta of n to the 0.753, which shows that size of this function will be 2 to the order n to the 0.753. And earlier I showed you from that corollary that deterministic size of this is 2 to the omega n. So this tells us that randomized size and deterministic size can be very far apart. Okay, but it seems that on the log scale things are still polynomially related. Okay, so that's where we ask the question like is randomized size and deterministic size polynomially related on the log scale? Okay. And with joint work with Arkadev, Nikhil, Jaykumar, and Swagato, we were able to show that the log of deterministic size and log of randomized size can at most be quartic apart, ignoring the polylog n factors where n is the input dimension. Okay. Now we studied the basic query model where you are allowed to query only variables. Now you can allow querying other classes of function, and this will give you more generalized query models. For example, you can say that the algorithm is able to ask parity of subset of variables. That will give you parity query model. Or you can say that algorithm is allowed to ask AND of subset of variable. That will give you AND query model. And similarly, you can define AND OR query model where you are allowed to ask AND of subset of variable or OR of subset of variables. And again, you can ask in these model of computation, what is the role of randomness? So in parity model of computation, one can show that for OR and AND function, the query complexity, randomized query complexity is order 1, while the deterministic complexity is omega n, which shows that parity query model of computation, randomness can give you tremendous saving. Okay. In AND query model of computation, we asked the same question. And this question was posed an open problem in a recent survey by Knoop, Lovett, McGuire, and Yuan. And we resolved this question with same set of authors, that the AND query complexity, deterministic AND query complexity and randomized AND query complexity can only be cubic apart, again ignoring the polylog n factors. And similarly for AND OR decision trees, we were able to show that randomness cannot buy you enough. It can only give you so much. For example, for AND OR decision tree, deterministic query complexity and randomized query complexity can be quartic apart. So I'll conclude, I guess. So I told you about some of the problems that we have been working on. The first problem is this deterministic size lower bound for composed functions. And we have now a method which proves the size lower bound in terms of properties of your inner function and outer function. Second is the type of problems that we looked on is this role of randomness in various query models. And we are able to show that randomness does not buy us enough on the log scale in terms of size in the ordinary query model. And in the AND query model and the AND OR query model, again, the randomness only buys you so much. They are polynomially related query complexities, randomized and deterministic query complexities. Yeah, thanks. Is there any question?